Good evening, and welcome to tonight's installment of the Silverstein Lecture Series, which is brought to you by the Center for Genetic Medicine here at Northwestern University. This lecture series is made possible by a very generous donation endowment from Herman and Bee Silverstein, and actually some of their family members are in the audience tonight, and I think it would be appropriate at this point to thank them for their generosity in making this possible. And the goal of the series when they started it was to bring advances in genetic research and medicine to the general public so that people could understand more about how the body works, how people work, and where medicine is going. And tonight we have a very different lecture in the area of human evolution. I think it really does not need a lot of explanation that to understand where we are and where we're going, it's really helpful to know where we came from and how we got here and what it means to be human, perhaps even. Okay. And to tell us about these things tonight is Dr. John Hawks, who is a world expert in human evolution. And Dr. Hawks started his sort of scientific career at the University of Michigan, where he got his PhD. And then he went to the University of Utah to do his postdoctoral research, where there's a really terrific evolutionary biology department. And then he went to the University of Wisconsin, where he has been since. And he has rapidly risen to become the Vilas-Borghesi Distinguished Achievement Professor in Anthropology. Along the way, he's gathered many awards, most of which I'm not going to tell you about, just list the highlights. He's currently a Fulbright scholar doing his work that he'll tell you about in South Africa, and he was just in South Africa up until a couple days ago. He has been a Kavli Fellow for the U.S. National Academy of Sciences, and he was a faculty fellow of the prestigious Howard Hughes Medical Institute. Okay, so he's been recognized in many ways in the academic community for his work. He has also, though, been very, very integral and prolific in bringing the work to the public, and he has been, and also in education. Okay, so he's been involved in 3 lecture series, at least one of which is a massively multiple online course, a MOOC, where there have been 41,000 students enrolled. Okay, so that's more than most professors teach in an entire lifetime. Okay. He has been either featured in or a consultant on 16 different documentaries for television or other media. So he is a go-to person for this area. And I found out today that he is also one of the authors of the questions on the high school AP exam human evolution section. So he is bringing his knowledge to the people in many different ways, and tonight we're very fortunate to have the opportunity to have him talk to us. So I give you Dr. Hawks.
Thank you so much. I want to thank the Silverstein Lecture Series for inviting me to this. I am a little bit out of the box tonight compared to probably the average lecture, because what you're going to hear about is relatively little genetics and relatively lot about fossils. And the reason why is, A, in my life, I always talk about the thing that I'm working on now because it's the thing I'm most excited by. And B, a lot of my earlier research on genetics has brought me to the stage of working on fossil samples as bioinformatic projects, as big data. And the site that you're going to hear about is the largest fossil hominin discovery that's ever been made in Africa. It's something that we're applying multimodal data recovery to, both in terms of the fossils that are represented, in terms of their spatial context, and ultimately in terms of biomolecules. We're now pursuing proteomic research, and we've made attempts but haven't yet had any success with DNA. So all of this stuff in human evolution has become massively interdisciplinary, multidisciplinary. We're working with a team of more than 150 scientists around the world, and the work that you're going to hear about has been contributed to by all of those scientists and by volunteers in the caving community and by our expert excavators underground. So this is a huge team effort. I'm going to tell you a story that, to me, I lived it, right? I was a part of it from the beginning. but it involves so many people with so many really, really important skills. I want to try to give you some of that in their own words. It's an enormous privilege to have been involved with the project from the beginning. We had National Geographic resources on site, but also resources from the University of Wisconsin to be able to video record and document the discovery from the beginning. It is, to my knowledge, the first time that we have an important fossil hominin discovery that has, from the very moment of discovery, video documentation of the entire process. And you're going to see some of that. It's a privilege for me because while I'm telling you about it and giving a presentation about it, I can also show you some of what happened on the site in the words and the voices of the people that were directly involved. And so I begin this with a short video where you're going to see the two cavers that were involved in the initial discovery of this site in the Rising Star Cave, and you'll hear from them and see the video that they generated during the course of that discovery.
Caving has always been great. Caving, you want to answer that question of what's around the next corner. That's like always the question you want to know. It's mostly fueled by curiosity. But as you get into caving more and more, the scientific side of it comes into it. You want to know, how did these places form? What happened here millions of years ago? What happened here billions of years ago? Basically, it creates a fascination with this whole environment. In my wildest dreams, I would never have thought that caving would take me to what's happening here. You could almost call this a bit of an accident. So my caving buddy and me, Rick, we were out exploring this cave on a Friday night. We'd gone into a very remote section of the cave, part that I'd never been in before, and in that section, well, we stumbled upon fossils. Yeah, at first we didn't exactly know what fossils yet. We started looking around a bit more until we found a mandible, and that was when we knew this was probably hominid. That was when we got excited about it. And since this discovery, it's crazy what's happening here.
So these guys were working with a friend of mine, Lee Berger. Lee is a National Geographic explorer. He's a professor at the University of Witwatersrand. He's really well known for his exploration of the fossil sites of the Cradle of Humankind area. This is just outside of Johannesburg, South Africa. It's a place that has generated, during the last 70 years, the largest fossil sample that we have of early human relatives and ancestors from the early stages of our evolution anywhere in the world. And Lee had found a site called Malapa. Malapa preserved in a very small ancient cave area several partial skeletons of hominins. And they belonged to a species that had not been discovered before. He named it Australopithecus sediba. And in this process of discovery during 2008, 2009, publication in 2010, he became very well known around the world for, we're reinvigorating fossil exploration in South Africa. The cavers began to become really interested in this kind of research because they're interested in caves. These guys that you saw, their thrill on the weekends was to go into deep parts of caves and squeeze through things that no one could squeeze through, right? So how many of you guys have been in a cave in your lives, right? A lot of you have been in caves, right? How many of you have been in a cave and they flip off the lights so it's like pitch black, right? Okay, that's the trick that they all do, right? How many of you had to crawl on your hands and knees through parts of a cave? Okay? How many of you have been in a cave where you had the walls of the cave or the floor and the ceiling of the cave actually squeezing on your body and had to squeeze through? Yeah, a few of you, right? That's something that if you haven't done this and you're susceptible to claustrophobia, right, is like the worst scenario, right? The earth is strangling you, sort of thing, right? And in fact, the cave that these guys were working in, the Rising Star Cave, was a cave that the caving community had been in and used for more than 50 years. And these guys, Rick and Steve, who you saw, right? Steve was talking to you, Rick you saw in the video. These guys don't get excited about caves like Rising Star. Rising Star is like their training cave. They take people in because you can get into these squeezes relatively close to the entrance, and you can learn caving techniques and so on. They get excited about a cave called Armageddon, which is probably the largest cave in the southern hemisphere, but we don't know how big it is yet because they're still working out where it goes, right? And so this cave they went into because they knew it already. This cave, the Rising Star Cave, which is underneath this hillside, is only a kilometer away from a site called Swartkrans, where we have found hominin fossils for the last nearly 70 years. It's less than 2 kilometers away from Sterkfontein, the largest fossil discovery site ever in Africa, and is also that same radius from several other fossil hominin sites. This is in a landscape which has been more intensively explored for fossil hominids than any other landscape in the world. Where you saw Steve squeezing down, and I'm going to show you another video of one of these squeezes in a second, right? Where you saw him squeezing down in that crack is this passage, which we call the chute. This chamber, what we now call the Dinaledi chamber, which contains hominin bones, was not on any map of the cave system. They didn't know it was there. We now know that cavers had been in it before. There's a survey marker in the cave, in the chamber, that shows us that someone had been in there. But it wasn't on a map. These guys didn't know it was there. And Steve, when they had climbed this jagged ridge called the Dragon's Back, they got to the top of it. Steve wedged himself down into this crack to rest. His boots weren't touching anything on the bottom, and he said, I wonder what's down there. And he went down, and that was a vertical drop of 12 meters, so around 40 feet, in a crack, and you guys saw it, right? In a crack that has a width at its minimum points of 7.5 inches. Everyone on our team who works in this chamber does that climb, and they all do it as a free climb. Ropes and safety harnesses actually catch on the rock, so they make it less safe. So everyone who works in this chamber have to fit down that. They fit down the first time. You saw the GoPro video that they shot. The floor of the chamber had bones. They brought photographs from the chamber out. They knocked on Lee's door after 10 at night. Boom, boom, boom. You're going to want to let us in. And in the process of it, they and the guy that had sort of contracted them to do this, Pedro Boschoff, showed Lee the photographs, and there were clearly hominin fossil bones in the photographs. They clearly weren't modern human bones. Lee sent them to me and a number of other senior colleagues that we have. We looked at them. We're like, this is not a modern human site. This is something that is genuinely fossil. It's something ancient. It was in a context that no one ever expected to find fossils. These fossils are laying loose on the floor of a cave. We could tell from the photographs that it was very likely that there was a large part of a fossil skeleton there. Right? We saw different parts of the body that were hominin. We didn't see anything that was repeated, so we thought, okay, this is going to be a skeleton like Lucy, right? It's going to be one of the most important finds that we've ever had because those partial skeletons are just so rare. I'll show you in a little bit just what we have for fossil skeletons like this. Lee seeing those and knowing that the caving community now, of course, was going to know these were there and they're open, accessible to someone who could do that climb, organized on short notice a dig to go into the chamber, recover these bones, and assess what was there. To do this, he realized he had a problem. He had to find people who could work in the chamber. 7.5 inches, I do not fit. Lee doesn't fit, right? In fact, there was no one on our regular sort of collaborator list that could do this. Some of them were afraid to go underground, right? Some of them just wouldn't fit. And it was just, you had to find new people with the right skill set for this. So Lee did exactly what any of you would have done. He went to Facebook and he put an ad on that said, I need the help of the whole community. Please reach out to as many related professional groups as possible. We need perhaps 3 or 4 individuals with archaeology, paleontological excavation skills for a project that may begin November 1st, 2013. This was sent out around the 10th of October, right? So he's saying in 3 weeks, we need you to drop everything, come to South Africa. The catch is this: you must be skinny and preferably small. You must not be claustrophobic. You have to have caving and climbing experience, right? Within a few days, 60 people applied, right? And this was a case where Lee has this for a long time had a personal assistant named Vilma who screens his emails. And she called him up and she said, "Lee, what have you done?" And Lee's like, what's the problem? "These women are sending me their dimensions." The vast majority of the people that applied were women, and it's a wonderful thing because of course, the filter here, having super archaeological excavation skills and being the right size, is much more likely. Although we had qualified men who had applied, but B, actually in our field, archaeology, anthropology, right now, 85% of the graduate student population are women. This is really the future of our field is a female future, and that's a wonderful thing. It means that when we found the best 6 most qualified people, we had this incredible group of young, all of them PhD students in archaeology from the US, Canada, Australia. It was really an international group, all of them united by having this sort of outdoorsy ability and having the right archaeological paleontological experience. And this established a theme that would carry through the rest of the project, that we're bringing in people, in many cases, who have no particular experience or expectation that in their lives they would work on a fossil hominin site. On the excavation side, we have a couple of these folks, our excavators who've worked on African anthropological sites, but Becca, for instance, is the shortest member of the team, who is a graduate student at American University in Washington, D.C., who does her archaeological survey work in the Great Dismal Swamp. She's a North Americanist. And Marina Elliott had not had any expectation of working on hominids. She had huge experience in forensic science and had done digs in Siberia for forensic archaeological purposes, was not particularly engaged in fossil hominin work in Africa at all. So bring in people, and this is going to carry through. You're going to see on our team of analysts who worked on the fossil bones that we have people with expertise in forensic medicine, people with expertise in anthropology of living human populations. The key is that everyone's bringing in this different experience set. And that's what makes us, as a team, incredibly rich. All right, I want to give you a little bit more cave sort of porn. This is the Superman's crawl that Rick is going through here. And it's called the Superman's crawl because if you go through it head first, you've got to put one arm up and one down, like Superman, in order to get your chest to fit through this. I think he's going to pop an arm here as he goes through it feet first. Yeah, exactly. You're seeing him squeezing his way down through there. This is also on the route to this chamber, and this is every time that any of our team members go into the Dinaledi chamber, what we at the time called the 101 chamber, because it was site 101 in our system, they're doing a traverse through the cave that takes from the entrance of the cave into the chamber a half an hour. And this is a distance of 120 meters, right? So imagine that you're doing the 100-meter dash or something like that, right? So you're running against Usain Bolt. And Bolt does it in 9 seconds. And you take a half an hour. Right? That's how slow and deliberate and difficult this is to get through. That's what our team does on their commute down to the chamber every day. So show you some scenes of the field work. We did an initial field season of 20 days underground. During that time, it really rapidly became clear that we were not looking at what we thought. after we had tested the systems, after we had shown that we could get safely in and out of the chamber and our recording systems were working, we could scan. We used a white light scanner to scan the entire floor of the chamber and to scan each individual element as we're removing it, because we can't fit actually theodolites and other traditional survey equipment into the chamber. So we're doing a scanning method. It's great because we can reconstruct from the top of the excavation to the entire area that we've excavated so far, every piece. And we put them exactly back where we recovered them. So the entire three-dimensional array of the site is preserved. We've got the data. We showed that all that worked. We recovered one bone. They came out. We looked at that jawbone, and we said, that's not what we thought it was. The second day of excavation, we put in a full day, and within 2 hours underground, our team had brought up parts of 3 right thigh bones, and it became clear that we were not looking at a partial hominin skeleton. We were looking at many skeletons. That continued. During the first week of excavation, our team began to dig, and by dig, I don't want to give you the wrong impression, right? Because a lot of archaeological sites you go to, many of you have archaeological experience, and you go to a site and you look at a dig site and they have this sort of nice clean profile where they've cut a meter into it and they've dug down a meter and you can look at the layers and so on. When I say dig on this site, we began where a skull was protruding from the floor of the chamber. And our team began to work around this skull with paintbrushes to very gently work around the outside of it to reach the point where we could bring it out, right? And that process of clearing around that skull, which very rapidly became clear to us, that skull was sitting upon a tangle of bones that our team began to call the puzzle box, because there were hominin bones stacked into hominin bones in such a way that you had to clear the entire surface of it to know if it was laying underneath another bone. That process took 3 days just to uncover enough of that skull that we began to think we could extract it. On the last day of that, the first Friday on the site, I get underground too, and I'm totally worthless. There's no reason to even have a photograph in the cave. My view of it's like this, right? I'm sitting, or Lee is sitting, at the command center with telephones that go down to the chamber, and we're talking to people down there. We're also controlling the safety through the cave. So at certain checkpoints in the cave, people have to call up and let us know that they've reached that. And then before they go down that vertical climb, they've got to call before they start, call when they reach the bottom, so that we know that people aren't sort of running into each other in that, right? And we're watching on video the process of the excavation. So as much as possible, we sort of joked that this is like working with astronauts, right? Because they're working in a place that we can't get to remotely, and we can talk to them and see what they're doing, but it really is a process that is remote. That's something that, as scientists, we can only know about by doing the science on it. So, as Marina and Becca were working on that last day of extracting the skull, and they were getting toward the end of the day, we would start around 7 in the morning underground, and 6 in the morning with a briefing. Around 7, we'd get underground. We would work in 2 shifts underground with sort of a middle zone of transition. And by 3 o'clock, that was the end of the day. And it was getting to be 3 o'clock the day that they were doing this. And I called down and I said, look, guys, I see what you're doing. I know you guys want to get that skull out today, but I see that you've got a couple hours work left on this. Why don't you knock it off and call it a day? Just give us another half hour. Okay, so I gave him another half hour. I called back down. I said, guys, I see what you're doing. It's not going to happen today, guys. And if you guys want, you can be the first ones in the cave in the morning, right? This is going to happen tomorrow. You guys can come out now. And no, we're not coming out without the skull. I said, guys, I got to insist. It's going to be a while. Are you going to come down here and get us? I'll never forget this moment, right? Because actually, no, I wasn't. And they did work another couple hours on it. And that day, our team, incredible case of teamwork, brought that partial skull out of the cave. They did a bucket line with a solid container that we had tested would fit through the chute. And it was really remarkable. And that was the kind of teamwork that we saw throughout the entire process. It's, for me, a unique experience because we're doing this incredibly challenging thing, and people really rise to the occasion. They're working together in incredible ways. So by the time our 20 days underground had passed, we had recovered more than 1,200 fossil hominin specimens. That was double the number at Sterkfontein, which to that time was the most numerous fossil hominin site in Africa. After another short week-and-a-half season of excavation the following spring, where we returned to recover some additional material, largely because as we left the site in November, and we had to leave, people's flights had been booked, we couldn't extend longer, it was a case where we had to close the site in a safe way. As we closed the site the last day, a hominin maxilla was protruding from the sediment that we couldn't safely extract. And we knew that we needed that for describing what these fossils were. We knew that this is something that's going to be anatomically really valuable. So we went back to the site, we extracted additional material, including some of the nicest fossils. And after that was done, we had recovered more than 1,500 fossil specimens. To date, in the Rising Star Cave system, we have more than 1,700 fossil hominin specimens. This is the largest fossil hominin discovery ever made in Africa. We're short only outside of Africa to the Cima de los Huesos site in Spain. I don't think we're going to catch them. Cima has at least 30 individuals in their assemblage. So far, we have 15, and we may have many more. Our excavation work to date, I described this, right, with the paintbrushes and everything. Every teaspoonful of sediment comes out of the chamber. We sieve through it. We have found tiny elements, including the middle ear ossicles in this sediment, and that's all preserved. We have all of that sediment still set aside. Our excavation area to date, if you guys are archaeologists, you'll understand, is an area about the size of a dishwasher door to the depth of about 20 centimeters. We have in the center of it dug deeper. We know that there's a sterile layer beneath our fossils that's not hominin fossil bearing, that extends down at least a half a meter. That's the net sum of knowledge that we have about the stratigraphy of the site. So this is something where there's huge investigation to come. To give you some perspective, the fossil hominin chamber itself is a little bit longer than this room is across and is variable in width, but it varies between about 1 meter and 2 meters. Our excavation area is about 0.8 square meters. So much, much left to come. As we left the site, we knew that we were going to have to approach this fossil sample in a different way than anyone else had. It was something no one else had recovered. Multiple partial skeletons of hominins, as it became clear to us as we were bringing out bones, of something we'd never seen before. As you guys will see, because I'll show you the bones, right? Different parts of this skeleton resemble different things. And it was a combination that we'd never seen. It had some traits that we'd never seen in any hominin population. It was clearly something different. And our question was, how do we study it? How do we understand what those differences are? Those of you who are anthropologists, anthropology students, know something about how anthropology has changed in the last 15 years, but those of you who aren't may not be as familiar with our field as it is now, as opposed to what you might have learned way back when, right? Way back when, in leaky times, there was this view that we as modern humans had come from ancestors that had been spread throughout the world, ancestors like Homo erectus, and that Homo erectus gave rise to Homo sapiens. And before erectus, there was a smaller-brained, yet tool-making species called Homo habilis. And Homo habilis gave rise to Homo erectus. And this was a very sort of orderly sort of evolutionary trajectory. Before habilis, there were Australopithecines, and those species that are part of the genus Australopithecus were multiple, and there were different kinds of them, and maybe they weren't all ancestors of us, right? Some of them looked sort of different, like maybe they were off doing their own thing. Today, the picture is vastly more complicated, and it's complicated for two reasons. Reason one is that we have found fossils that don't fit that simple picture. The Neanderthals are sort of a first clue, right? Neanderthals are a species that lived outside of Africa in the western half of Eurasia between about 500,000 years ago and around 30,000 years ago, and look pretty different from most of us today. And the idea was that sort of recently, there was this group of people, the Neanderthals, and they might be something different from us, modern humans, we call ourselves. As the fossil record developed, there were other sort of different-looking things that also seemed to have lived around the same time that modern humans were originating, or Neanderthals were living. Right? We call them archaic humans. We used to think that all these archaic humans were sort of derived from Homo erectus, and maybe they are, but it's become clear that there were different kinds of things that are really different from any of us. Things like Homo floresiensis, a species that lived on the island of Flores that had a very small brain, very small body size, and persisted up until around 40 to 50,000 years ago. There were lots of different kinds of people in the world, not all of them very much like us. Before that, Homo habilis is still something that we talk about, but we've got other fossil species that also look like sort of primitive members of our genus. Homo rudolfensis is one of them. Australopithecus sediba, the one that Lee found in South Africa, another one. Australopithecus sediba we call Australopith because below the head, it doesn't look like it was really well suited for long-distance walking. So we say, well, Homo, that has to do with the brain, but it also has to do with behavior. And Sediba's got a small brain, but it doesn't look like it walked long distances like we do. Its legs are short, its feet looks like they're well made for climbing. This is something different from us, even though its teeth and its face look a lot like humans. And the way in which the fossil record has become more complicated is by finding these things that don't seem to fit some linear arrangement of becoming more and more human-like. Instead, it seems like they go off in their own direction. Something like Lucy's species, Australopithecus afarensis, seems to have gone off in its own direction for a while. And that kind of thing we look at and say, this is more than just a lineage. This is like a tree. It's like a bush. The other thing that's made our field much more complicated is the recognition from ancient DNA that some of these different kinds of hominids mixed with each other. Even though they look pretty different, they're still breeding at their boundaries. That breeding is not in large amounts in any case that we've found so far. Neanderthals contributed between 2 and 4% of many of the genomes of people in the room. For people who are in East Asia or have ancestry in East Asia, it's on the high end of that. For people in Europe, it's on the low end of that. For people in sub-Saharan Africa, it's much lower. It's 0.1%, but it's not zero. There's another population that we've discovered from ancient DNA called the Denisovans. And that population, which we only know about from genetic evidence from tiny bones, including the bone of a finger from Siberia, it's really different from Neanderthals, but also contributed some DNA to living people. In this case, the maximum amount in living native Australians and people of Highland New Guinea. So on the very southeastern end of the old world, there's this influence of this other population that has a very, very small influence on other populations in the world. So these populations are mixing with each other. We as yet have no ancient DNA evidence from any African population sample. But we know from the DNA of living people in Africa that there's a similar kind of complexity that arises. The reason why is that once you find that Neanderthals have contributed to our population and you say, that's what it looks like when you have some DNA from some ancient group of people. You can look for that signature in people without having the ancient genome. You could say, people in Africa look like they've gotten some of their DNA from some other ancient groups of people. In particular, hunter-gatherer peoples of Africa today, Pygmy peoples of the Congo rainforest, Kungsan people of southern Africa, Hadza people of East Africa, those populations have some DNA from some other peoples. Again, a small amount, a couple of percent. But what we're looking at is evidence of what geneticists call ghost populations. Populations that we only know about from the traces that they have left within our genomes. And those populations that once existed, we as anthropologists are challenged to try to discover which fossils, if any, might belong to them. With our fossils, with Naledi, that's a question that comes to mind, right? Are they connected to us? And what evidence would we look at to try to judge that? But as a tree of our evolutionary history today emerges, it's clear that we have branches in the past that we didn't know existed because we hadn't found the fossils yet. And we know that there are branches that we haven't yet identified because we see the ghost population signatures in our living people's DNA. And we know that all of these branches are potentially mixing with each other to slight degrees. That's a cool picture. When I talk about Neanderthals, it's cool because we're finding evidence of their biology inside of us. We can discover stuff about them that we could never do if we didn't understand the genetic picture. But when I address an unknown sample of fossils from Africa, I have some very different questions in mind. How can I connect them or evaluate their relationships to the known skeletal record? And I want to tell you all, the skeletal record of our evolution is really big. We have a lot of skeletal evidence of human evolution. But it has really, really biased, weak spots. We know a lot about Neanderthals. We've got skeletons and skeletons of Neanderthals, right? We know a lot about their biology. We can look at their biomolecules, huge amounts about them. We know relatively little. We know a lot. Let's say another thing. We know a lot about jaws and teeth, right? Earlier in hominin evolution, we know a lot about teeth. We get lots and lots and lots of teeth of all of the species on that tree and more. What we have very little evidence of is the entire skeleton of species that predate Neanderthals. These are the fossil hominin skeletons that exist before 1 million years ago. It's not a lot, right? When I said when we found a fossil hominin skeleton in this cave, it was going to be a giant discovery, right? That's because of this. This is the Turkana boy, the best skeleton of Homo erectus. It's about 1.5 million years old from Lake Turkana Basin, found by Richard Leakey and Alan Walker in 1986. This is Lucy, found by Don Johansson and Tom Gray in 1974. This is a male partial skeleton of Lucy's species. His name is Kadanumu, and he is found by Johannes Haile Selassie's team in 2007. This is a partial skeleton of Australopithecus africanus from South Africa. It's probably around 2.5 million years ago. Lucy's species, over 3 million years. These are the two best partial skeletons of Australopithecus sediba from South Africa, around 2 million years old. This is the evidence. And why are these sorts of things important? I love fragments, right? I love figuring out what part of the skeleton is represented by a part of a bone and evaluating its anatomy compared to other things. But the problem with fragments is that you can't tell how the different parts go together. If you want to evaluate a fragment, you have to assume what species it belonged to and try to put it into some arrangement with the other species that exist that preserve the same anatomy. If you want to evaluate those things independently, you need more of a skeleton of one individual. The evidence from the Dinaledi chamber is this. We have, in this chamber, more fossil evidence of any fossil hominin species other than Neanderthals. Suddenly we have a data set that represents the entire anatomy of a skeleton of a population multiple times, that represents at least 15 individuals in this chamber, that is representing every stage of life from neonate to the oldest individuals that we have with teeth worn completely down. Suddenly this gives us a picture that we have from no other species. And that poses enormous challenges. Right? How do we deal with something that we actually have more evidence than we have of almost anything else? We were able, through the funding of the National Research Foundation in South Africa, to bring more than 30 early career scientists, people who are finishing their PhDs or who have started on their first assistant professor postdoc positions, to South Africa, including South African scientists, Ethiopian scientists, scientists from Australia, from America, from Europe, brought them from all over the world, put them together with experienced people who'd been working on the Sediba project, me and a number of my other senior colleagues, to study the fossils for 5 weeks and to figure out what they were. We brought experts in every area of the anatomy. We brought experts who only study the foot, and who only study the hand, and who only study the curvature of the fingers, and whose research, in other words, has data sets that have been developed with the best comparative samples to come together to come to a comprehensive description of what this fossil sample might be. In the course of that, we concluded that these fossils, while parts of them could be compared to many other species, as a whole, the anatomy that they represented was completely unique. They could not be matched by any existing species of hominin. For that reason, we named them a new species, Homo naledi. And naledi means star in the Sesotho language, which is one of the languages spoken in this part of South Africa. So, the star people. The anatomy of Homo naledi is a very strange mixture. Anthropologists who know the fossil record look at this and say, how the heck did you find this weird combination? I'll give you some indications of that, right? If we look at the skull of Homo naledi, its skull is shaped on the whole sort of like a Homo erectus skull. Right? It's got, for instance, a brow ridge that sticks out in front of its face with a groove behind it, a sort of a curving sort of forehead, and large lines on the skull for muscle attachment, but not lines that meet in the midline, lines that are marked on the side of the skull. These are sorts of things we see in Homo erectus. However, its brain, when we reconstruct its size, is smaller than Homo erectus by a substantial extent. With a brain size between 450 and about 550 cubic centimeters, its brain is the largest ones equal to the very smallest specimens of erectus we've ever found. It's smaller than the brains of Homo habilis. This brain is equal in size to the earliest hominins that we have. Its brain is about a third the size of yours. So it has a Homo-like skull configuration with a smaller brain. This is John Gurtsch's work. John's a paleo artist. He's a friend of mine, and he's one of the best in the world at trying to figure out what in life these species might have looked like. This is, I think, the best that we can do for what Homo naledi looked like as a living creature. And obviously, artists have to, speculate about some details, but to the extent that there's speculation, the patterning of facial hair and that sort of thing, it's based on what we see in living humans and other primates. So it's an educated guess. The teeth, we have more than 190 teeth from the site so far. They represent at least 15 individuals. Here's the teeth of a toddler age individual, around 2 years old or 1.5 years old. Here's the teeth of an old individual whose teeth are worn completely down at the roots. We have every life stage in between. We have at least 8 children and 7 adults in the site. They represent the entire life history. The teeth are, on the whole, very human-like. One of these teeth If I shuffled it into a set of human teeth of the same type, you might not notice it. Our tooth experts say, well, that tooth is really human. However, the premolars here are very different from any of your premolars. The canines also have some features that distinguish them from modern human canines, and the size order of these teeth is totally different from yours. The first molar is the smallest one, the second is larger, the third molar is the largest. I guarantee maybe there's one person in this room who has third molars that are bigger than the others, but it's very, very rare. This is a very primitive hominin trait. It's true in this species, as it is in Australopiths. We have a primitive dentition, in other words, of human size. And that's something that, again, we haven't seen before. Beautiful, beautifully preserved teeth. If I show you the hand, here's a hand in sight, in articulation. You can see all the bones of the hand and wrist here. The finger bones are curled over like this. Right? This hand was as it was in the sight. And when we put it together, you'll see that it's a remarkably human-like hand in its proportions. Its thumb is proportioned like your thumb in length. Its fingers have broad fingertips like yours do. Its wrist bones are nearly identical in morphology to your wrist bones. This is a very human hand with a very oddly shaped thumb. Its thumb, while it's the length of ours, has a very broad connection to the palm, and the bone that roots that thumb in the palm is very narrow at its base. Most metacarpals, first metacarpals of that kind that you see in hominids, apes, other kinds of species, are like a cartoon dog bone. They're sort of equal on both ends and narrow in the middle. This is like a chicken leg. It's narrow at the base and wide at the side. And a lot of times people ask us, how do you really know that this strange mixture of things is not just a jumble of different species all jumbled together, right? How do you know that this isn't multiple things and you're looking at it looks jumbled because it is jumbled? The reason we know is that when we look at unique features like this, we have many copies of them and they're all the same. If we had a jumble of different bones of different kinds of species at one site, we wouldn't find that we had all premolars from one species and all thumb bones from another species, right? You'd have a jumble of things. In fact, every anatomical feature that we have here that is strange, we have in many copies. And that gives us great confidence that what we're looking at is a sample of a population that once existed, a population that was just different in the makeup of its characteristics. Its finger bones are super curved. This is very much different from your finger bones. They're using their hands. Even though their hands are anatomically like ours, they're using them probably for climbing. That's what exerts the forces that create that curvature. The legs and feet of Naledi are long and skinny, and that lets us estimate body size and stature. Naledi stood between about 4.5 and 5 feet tall. So they're the size of small-bodied humans. Some of you, how many of you guys are 5 feet tall in the room? Yeah, you're out there. This is actually average for some populations in the world. It's not average for the American population, but it's not odd to be this height. And their weight is between about 40 and 55 kilograms. So between about 88 and 110 pounds. So human-sized, with a brain a third the size of ours. Their femora, however, and their hip joints are very primitive. They're like Lucy's femora. So even though they have long legs and, I want to point out, incredibly human-like feet, with toes proportioned in a way that ours are, the little toe bones are not here. We have most of them, but our foot experts can't figure out which are which. It's because actually those little toe bones are basically anatomically the same, and you actually can't tell which are which. I don't blame them. It's just the way it is. But the foot on the whole is entirely human with its arches, transverse arch. I like this picture of the metatarsals because you see that arch, right? That's there. My student, Zach Throckmorton, I love this story, is now an anatomy professor in Tennessee. And he came to work on the foot bones. And one day he's studying these foot bones and he says, "Why did you bring me here?" And I said, "Isn't it amazing? You've got 107 foot bones of a fossil hominin species that nobody's discovered before. It's so cool." And he says, "These bones are completely unremarkable." And I said, what do you mean? "They could have walked into his dad's a podiatrist. They could have walked into my dad's practice." I'm like, the feet are human feet, even though the rest of the body is not. And that's a sign of this odd mix of characteristics. When you have consistently, again and again, the same strange mix that we've never seen before, you know you're looking at something quite different. And what you know is that the picture that you thought was true, that these things are logically connected to each other. Species with more human-like feet should also have more human-like brains and more human-like teeth. It's actually not true. These species have evolved along trajectories that had very different pathways in terms of adaptation and probably genetic drift. And those pathways have caused them to vary in ways that don't make sense if you thought that there was a linear arrangement of characteristics. So here's Naledi on the right with its small head and its shoulders that are actually oriented upwards like this, but a human-like body size, compared to the Turkana boy Homo erectus skeleton reconstruction and Lucy's reconstruction. So I think this is a really nice job of what Naledi would have looked like from a distance. If we try to place it on a tree, we tend to focus on features of the skull and teeth because we have those for most other species. And we don't have the kind of evidence of the rest of the skeleton for many species. And so when we look at those features, it looks like it fits at the base of our genus somewhere around the origin of Homo erectus or between erectus and habilis. The hand is more human-like than habilis's hand, but the skull is clearly more primitive looking than erectus's skull. So we put it there, but I put these question marks on this chart really deliberately because in every one of these cases, it depends on what we think about the skull and teeth. And in fact, the rest of the skeleton is telling different stories. Different stories, because some parts are telling one story and other parts are telling a different story. We don't know which parts to trust. And that means that our family tree right now really does have a lot of question marks on it. One of the biggest question marks with this is the date. We have not yet been able to publish or announce to the public how old the fossils are. And initially, of course, this was very difficult because the traditional signs that we would rely upon to know what species, how old they weren't there. We were working in a soft sediment that wasn't mineralized, that wasn't hard. We'd never found fossil hominins in this context before, and so we didn't know. We found the bones of Homo naledi completely alone, without the bones of any other animal species. And without that, we weren't able to say what extinct species were with them, and so we couldn't figure out how old they might be. We're coming to the point where very soon we'll be able to publish how old they are. I will tell you that the age of Homo naledi is completely unexpected. This is the Vice President of South Africa at the announcement that we made in 2015 of this species. It is really, really great to be involved in a project where you have that kind of support from government, where not only is there sort of some funding support for this, but also they see the importance of this as a country, right? Cyril Ramaphosa, some of you who know the ANC or the history of South Africa know the importance of that. And to have someone of that stature come and say, this work is helping to establish a scientific basis for a common humanity in the context of South Africa and its history is a really, really powerful thing, right? Our science looking into human origins, showing that we share this heritage, and discovering how that heritage is connected to living people in our populations, that has real importance in the world. It helps to frame how we think about ourselves as a species. It shows how much we share and how we share the planet and have done for millions of years. And so to have that recognition and to see it making a difference, at World Heritage Site level, at a Ministry of Tourism level, at a school level, with questions about Naledi Sediba on the matric exams in South Africa, that shows the impact that we as a project are able to have. It, of course, has a huge public impact in the U.S. and around the world. I love to point out that whenever you have something cool that you announce that gets a lot of press, it's in the funny pages. And it's pretty awesome, actually, when that happens. But my favorite is the South African version of this because it's all about rugby. And Naledi marching on the field with its million years of experience. The Springboks that year needed it. They didn't do so well. But much more important is the impact that we have on the public. We put the fossil hominin remains on exhibit at the time that we announced the existence of Homo naledi, and during the first months that they were on exhibit, limited time, we had an increase in visitorship at the World Heritage Site by more than a dozenfold. And next month, April the 18th, we will be returning the fossils to exhibit at the World Heritage Site with new discoveries, and that exhibition will be open probably for most of the next year. So if you have traveled to South Africa, this is really the time to engage with this history, to see the new fossils, to see the sites. This is really a unique time in the history of our field because these discoveries are going to continue. We have moved from a field in which the best you could hope was that you might discover a hominin tooth, and that would make your name for history, right? To where we're recovering real samples of fossils that we didn't expect existed in exactly the parts of Africa that have been most extensively explored. There are a lot of caves out there. Our teams are now working full-time in the cradle area and have already uncovered more fossil sites. We are moving to develop cave exploration in other parts of Africa and other parts of the world, and that will find things that we have never yet looked for. This is a time of discovery. The field is really changing. It's changing from a technological basis, from a biomolecules basis. Our ability to say things about these populations is magnified to pure discovery. We're going into places that people haven't been before, and we're finding new stuff. And that's exciting. It's engaging a broader selection of scientists from all fields, and scientists, young scientists, engage in our project in the process of discovery. So it's a really, really exciting time. I will say that you can download these fossils. They're on the site Morphosource, and you can download the shapes of them and print them. I've got a bunch of prints here with me if you guys want to see prints. It's an exciting time because you can engage with these. You can get them out to your classrooms. People are printing them all over the world. And one last thing to say. A lot of you want to know how the fossils got into the chamber, right? Right? This is an extraordinary setting. It's a setting that we've never seen before. These fossil hominins are there, and it's only Homo naledi. We don't have other kinds of large animal species there at all. We've got a few mouse teeth. That's it. And that's a situation that's unique. We have articulated remains. So we know that these entered the cave as bodies. The bodies, the skeletal remains that we have are commingled. They are not laid out. They haven't been buried in the sense that nobody dug a hole and put bodies into a hole and covered them up. They were once an assemblage of bodies that are partially commingled today. There is no sign on any of the body parts. No bone has a mark from a carnivore. There's no tooth marks. There's no breakage. There's no fresh green breakage on the bones at all. They were not carried by water. There's no rounding of the surfaces that would happen in water. There's no size sorting that would happen in water. They weren't carried any distance. The cave has a sealed chert roof that has no other openings in it. The fossils came in the way we did. The sediment inside of the chamber has a different consistency and chemical setting from the neighboring chambers. The neighboring chambers have external sediment in sand particles that have come in from outside the cave. This does not. Everything in this points to excluding the explanations that work at other sites. What we're left with is Homo naledi put bodies in this chamber. At the moment, it's our best hypothesis. It's the one we can't reject, but it does pose problems. How did they do this? What was the contour of the cave like in the past? Were they using other parts of the cave? Was it different in the past? Did they have light? Those are all questions that we're working really hard to answer. Okay, if you want to read more about this discovery, we have a book coming out next month, Almost Human, me and Lee Berger. And that's the talk. I'm happy to answer questions, and I'll take a few. I've run longer than I did last night, right? So I do want to have a chance for the reception. But let me take a few questions, and then I'll shuffle outside, and we can talk more informally as well. All right, question in the middle there.
Thank you very much. Do you have any notion over what period of time the bodies were deposited?
We know that they were not deposited. The question is, over what period of time might the bodies have been deposited? We know relatively little about this. We know that they weren't deposited simultaneously because the way that the bones lie in the sediment, it's clear that some of them arrived early and others must have filled around. So it seems clear that there was some period of time involved, but we don't know how long. The anatomical similarity of the different parts is really, really impressive. They look like they represent a single small population in terms of variability. So our null hypothesis is this is maybe a population that of individuals that had a practice that knew each other, and you're looking at some period of time, but probably, generations as opposed to thousands of years. But we really don't know. Even with the information that we have now about geology and in the overall date, we really don't know how much time is involved.
That would suggest that they had some residency in the area rather than just being nomadic all over the place.
This is the idea is that maybe they lived there and were resident in the area, and that's sort of how I feel about it. They knew this cave. This is a place that they returned to again and again. It wasn't lots of groups. They were using the cave as part of, I think, a culture, and that speaks to them actually occupying space around it. We will investigate that with stable isotope data. We can get strontium and other stable isotopes out of them that reflect the geology and that sometimes give us some evidence about mobility and residence. We'll see what these bones have to say, and based on that, we'll maybe test the hypothesis. Yes?
So based on different credentials as to what they ate?
Yeah. The question is, can we tell what they ate? So far, we haven't done stable isotope work on the teeth. That's one of the things that we use to determine diet. We also have almost no calculus left on the teeth. You guys might have seen in the news yesterday, there's a story about Neanderthals and what they ate. The way that we find that out is by sampling the mineral layers that build up on the teeth. Your dentist takes those off for you. But if you looked very carefully under a microscope at them, you would see the tiny granules of starch from potatoes and the tiny plant pieces from spinach and other sorts of things that actually catch in that. And we can figure out a lot about diet from that. We have almost no calculus adhering to these teeth. They're incredibly clean. They've been to the dentist. And as a consequence, we so far know nothing about it from that angle. The morphology of the teeth is compatible with an omnivorous sort of diet, the same sort of diet that humans and many other kinds of fossil hominids have. And we will likely learn more, but so far we don't know. Yes?
And there's no residue of food or clothing in a restaurant?
There are, in fact, no artifacts whatsoever. There's no stone tools. There's no bones of animals that might have been part of the diet. This is one of the things that leads us to believe that this chamber was not a residence place, but was used in this sort of special way.
Does it flood?
The groundwater levels alter today, and we're not very, very far above the groundwater level. We believe that sediments may have been inundated in the past, but we're not sure, and we're still working to investigate that. There is flowstone formation in the cave at intervals. That tends to happen in wetter periods, and the fact that the flowstones have formed in the cave in the past points to the fact that water wasn't, above them for a long time, because they would have dissolved. Yeah?
You mentioned that you found teeth from toddlers and elders. Is there a way to tell how old the elders were?
So teeth that are worn completely down in fossil contexts are at the end of their useful life, right? And in fossil populations, that's different from today. There are folks in the room here who are 70 years old who have perfect, almost unworn teeth. And this is because our particular westernized American diet doesn't exert a lot of wear. A natural foods hunter-gatherer diet wears the teeth. And in these fossil populations, we tend to think that individuals who have their teeth worn to that degree are in their late 30s to 40s in age, but we're very imprecise when we start talking about age in that way. They could easily be much older, they could potentially be younger. There's a bracket on how young they could be because we have adults that have a certain amount of wear and have erupted all their teeth. So you know that, well, these totally worn ones are not, their third molars haven't just come in. They've got maybe 20 years of wear or more on them, but beyond that, it's hard to be precise. Any other questions?
Okay, let's thank
All right, thank you.
Dr.